Hello everyone, welcome back to linear algebra. In this video, we're going to talk about coordinate systems. So what do we mean by that? Previously, we've learned the definition of bases. So let V be a vector space over the real numbers, and let V1 through Vp be a set of vectors of V such that one, we say that the sets in B, the vectors in B are what we call linearly independent. And two, the vectors in B span all of V. So the span of the vectors V1 through Vp, which is a vector subspace of V, suppose that that is the span of all of V. They span all of V. Then we say that B is a basis of V. Okay, great. So for example, just the simplest example is that for R3, we have the canonical basis. So the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1, they are a basis of R3. And this, we know that this is very useful in that they span all of R3. So the span of B is all of R3. And in fact, we know that every vector in R3 is easily a linear combination of these vectors because is A times the first vector, B times the second vector, plus C times the third vector. Clearly, they span all of R3, and clearly one can show that these vectors are linearly independent. So it's easy to prove that this is a basis in this particular case. But what I want to emphasize here is that this is a unique expression. This expression is unique, which is something that is easy to prove in this case, because if I have x 1, 0, 0 plus y 0, 1, 0 plus z 0, 0, 1, and that is exactly ABC, well, this is certainly, if I just scale and multiply, this is the vector x, y, z, and that implies that x is A, that y is B, and that z is C, and that is the unique solution to that system. But what if I have another basis? So if I have another basis of R3, for example, B prime, 1, 0, 1, 1 minus 1, 0, minus 1, 0, 2, this is also a basis of R3. How do we know that? Well, I can make a matrix with all those vectors, 1, 0, 1, 1 minus 1, 0, minus 1, 0, 2, and row reduce it. If I row reduce it, I get 1, 1 minus 1, 0, minus 1, 0, and I'm going to reduce the third row. This is 0, minus 1, 2 minus minus 1 is 3. So I get now 1, 1 minus 1. Let's change the second one by a sign. And now I can row reduce the last one. 1, 1, minus 1, 0, 1, 0, 0. Add to the third one the second row, and I get 0, 3. And now I can already see that this has 3 pivots, 1 in each row and 1 in each column. And in particular, first of all, the system AX equals 0 has a unique solution because there is a pivot in every column. And this system AX equals B for any B in R3 also has a solution because there is a pivot in every row of A. Okay, so this first condition, let's say 1 implies that the set B prime is linearly independent, while the second condition shows that B prime spans all of R3. So therefore, they are a basis of R3. And now my question is, if I can express just every vector B can be expressed as a linear combination of these three, but is that expression unique? Well, it turns out that it's not only true that there is a solution, there is in fact a unique solution because there is a pivot in every row and in every column. So let's see that in action. So for example, can I have, let's say, 1, 0, 1 plus y times 1 minus 1, 0 plus z times minus 1, 0, 2. Can this be 1, 0, 0, and in how many ways? Well, if I'm going to do that, then I can write an augmented matrix, 1, 0, 1, 1 minus 1, 0, minus 1, 0, 2, augmented to 1, 0, 0, and see what happens. This is 1 minus 1, 1. Again, 0 minus 1, 0, 0. If I row reduce the last row, I get 0, minus 1, 2 minus minus 1 is 3, and then I get a minus 1 in the augmented column. These will be 1, 1 minus 1, 1, 0, 1, 0, 0, 0 minus 1, 3 minus 1, and that row reduces to 1, 1 minus 1, 0, 1, 0, 0, 0, 3, 1, 0 minus 1. And now I could just keep going and actually find the solution. Maybe we should do that. 0, 1, 0, 0, 0, 0, 1 minus a third. And that gives me now row reduce this position here. That is going to be 1, 0, minus 1, 1. 0, 1, 0, 0, 0, 0, 1 minus a third. And now I can row reduce the last spot, row reduce, eliminate this element here, 1, 0, 0, and then 1 minus a third is 2/3, 0, 1, 0, 0, 0, 1, 0 minus a third. So this tells me that x needs to be 2/3 and y needs to be minus a third, which let's see if that is true. So 2/3 of 101 minus a third of minus 102, that would be 2/3 plus a third is 1. 2/3 0 minus a third 0, that's 0, and 2/3 minus 2/3 gives me 0. So yes, that is true. And you can see that in fact there is a unique solution. There was no pivot in the augmented column, so it's consistent. there is a pivot in every column, so there's a unique solution, and therefore we have a unique solution. Um, what I got here was that z is minus a third and y is 0. That was the unique solution to the system. So is it true that for any basis, the expression of one element in terms of that basis is unique? And that is, in fact, a theorem that we're going to prove next. So such a theorem is called the unique representation theorem. The unique representation theorem, and it says the following: let V be a vector space, and suppose that B with elements B1 through Bn as basis elements is a basis of V. Then for each V in V, there is a unique solution of the equality that V is lambda 1 times B1 plus lambda n times Bn for some unique scalars lambda 1 through lambda n in the real numbers. So let's prove this theorem. Why is that true? Well, the proof, first of all, since B is a basis of V, then by definition of basis, we know that the span of B is all of V, and in particular, since V is in V, there must be a linear combination of the vectors of the basis of B1 through Bn such that that is equal to V. So there are lambda 1 through lambda n real numbers such that V is lambda 1 B1 plus plus lambda n Bn, because that is what it means to be a linear combination and for V to be part of the span of those vectors. But now, so this would show the existence, and now we want to show the uniqueness of such an expression. That's the interesting part, is that it gives me a unique expression. So suppose there are two expressions. So suppose that V is lambda 1 B1 plus lambda n Bn, and suppose I have a second expression, mu1 B1 plus mu n Bn for some scalars lambda I in the real numbers and mu I in the real numbers. So I have two different expressions. Then I can put oranges with oranges, so the B1s with the B1s. So I'm going to bring this expression to the left-hand side, and that would give me, if I take a common factor of B1 in the scalars, this is lambda 1 minus mu1 B1 plus lambda 2 minus mu2 B2 plus plus lambda n minus mu n Bn is the zero vector. But now what I see is that this is a linear combination. This is a linear combination of B1 through Bn that is equal to 0 to the 0 vector, but the B1s, the B1 through Bn are linearly independent. And that tells me that such a linear combination must be that every scalar is 0. So every one of these coefficients has to be 0. Lambda 2 minus mu 2 has to be 0, and all the way to lambda n minus mu n has to be 0. But that tells me then that lambda 1 is equal to mu 1, lambda 2 is equal to mu 2, etc. So the lambda i's and the mu i's are precisely the same numbers, which is what I wanted to prove, because I wanted to show that these two expressions for v are precisely the same expression, and that's what I just proved, that every coefficient for v1 is exactly the same. So I'm going to write v as a linear combination. There's only one way of doing it, which gives me the concept that this expression is actually some coordinates for the vector in terms of the basis. And we're going to use that to write coordinates for any vector space. We're going to find a basis and then use that to write coordinates. So, for example, here is the polynomials, let's say, of degree less or equal to 3 over the real numbers. So these are polynomials of the form a plus bx plus cx squared plus dx cubed, where a, b, c, and d are real numbers. This is a vector space, and it has a basis, which is the basis 1 x, x squared, x cubed. And we know that every polynomial can be expressed uniquely in terms of this basis, because any polynomial, a plus bx plus cx squared plus dx cubed, is precisely a times the vector 1 plus b times the vector x plus c times the vector x squared plus d times the vector x cubed. And this expression is unique. And now if I have a different basis of vectors, then, well, I would have a different expression for a different, if I have a different basis for this vector space, I would have a different expression, but the coordinates would be unique with respect to the new basis. So these coordinates, so what I'm going to say is that this vector, in terms of the new basis, is going to be the vector a, b, c, d with respect to 1x, x squared, x cubed. So I'm going to translate expressions in polynomials, which are hard to work with, into vectors that I can work with. So these are the coordinates of the polynomial. If this is the polynomial p of x, with respect to that basis. So let's define that more concretely. So we're going to have, so let V be a vector space, and let B be a basis of V, and let V be in V with an expression. V is lambda 1 B1 plus lambda n bn, where those are the vectors in the basis are b1 through bn for some unique lambda 1 through lambda n in the real numbers. Then we define the coordinates of v with respect to the basis b to be the vector that is given by those coordinates, lambda 1, lambda 2 through lambda n are the coordinates of v with respect to the basis b. So for instance, For instance, if we have R3 and my basis is the usual basis 1, 0, 0, 0, 1, 0, 0, 0, 1, then if I take V to be the vector 1, 0, 0, then the coordinates of V with respect to the basis B will be, well, if I write this vector as a linear combination of these three vectors, that will give me the coordinates. So this is 0 times 1, 0, 0, no, 1 times that plus 0 times 0, 1, 0 plus 0 times 0, 0, 1, right? So the coordinates will be 1, 0, 0 with respect to the basis B. But if instead we work with this different basis we had a moment ago, which was, let me go back to my notes here. So if I instead work with R3 and my new basis is the basis 1, 0, 1, 1 minus 1, 0, minus 1, 0, 2, and V is again the vector 1, 0, 0, then we just saw that 1, 0, 0 was, what was it? So it was in coordinates, it was 2/3 of the first, 0, and then minus 1/3 of the third vector. So it is 2/3 of the first vector plus 0 times the second vector minus 1/3 of the third vector. So what that tells me is that now the coordinates of this vector v, so the coordinates of 1, 0, 0 with respect to this new basis b prime will be this, and that. Okay, so they will be 2/3, 0 minus 1/3. So these are the coordinates with respect to our new basis. And that allows me to talk about every vector, but with a different coordinate system. This is a different coordinate system that, of course, this one is usually the Cartesian coordinate system is a lot easier to work with, but there might be situations for whatever reason, for example, for physical reasons, that there are forces in these directions, and this coordinate system is a lot more useful than the usual Cartesian coordinate system. And with respect to this system, I want to know what are the coordinates of any vector. So for example, that vector, I can translate it to this coordinate system using this function that gives me the new coordinates. For example, if I'm talking about polynomials, say of degree up to 2, over the real numbers, and I take my basis to be the usual basis, 1x x squared, and I take a polynomial that is the polynomial 3 plus 7x minus 2x squared, then the coordinates of that polynomial with respect to this basis, the usual basis for polynomials, will be 3 times 1, then 7 times x minus 2 times x squared. And this allows me, so these are the coordinates with respect to b, and this allows me to work with polynomials as vectors because I know how to do things with vectors very quickly and very efficiently. So that will allow me to do better computations in the future. So for example, I can also just talk about a matrix 1, 2, 3, 4, 5, 6. This is a matrix in the 2 by 3 matrices with real coefficients, and I can come up with a basis of this space. So here's a basis, would be what we would call the canonical basis in this case, 0, 1, 0, 0, 0, and 0, 0, 1, 0, 0, 0, dot, 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 up to the sixth matrix, which looks like this. And then I can write coordinates for these matrix. It will be well, 1 times the first vector in my basis, 2 times my second one, 3, 4, 5, and 6. Because if I do 1 times 1, 0, 0, 0, 0, 0 plus 2 times 0, 1, 0, 0, 0, 0 plus up to 6 times 0, 0, 0, 0, 0, 1, that gives me V. So these numbers would be the coordinates that I'm looking for, and those are the coordinates that appear in the coordinate vector. How do we find these coordinates? So how do we find coordinates? So for example, let V be R3. We're going to take as a basis to be the basis we had before, 1, 0, 1, 1 minus 1, 0, and minus 1, 0, 2. And now I want to take a vector, for example, the vector 1 minus 1, 3, and we want to find the coordinates of V with respect to B prime. So what I'm looking for is a three-dimensional vector. So there will be an X, Y, Z such that, well, X times the first vector in the basis plus Y times the second vector in the basis plus Z times the third vector in the basis gives me the vector V that I'm looking for. So these X, Y, and Z will be the coordinates with respect to these bases B prime. And I can write this as an augmented matrix. This is 1, 0, 1, 1 minus 1, 0, minus 1, 0, 2, 1 minus 1, 3 is the matrix for the augmented, is the matrix for the, or the augmented matrix for that system. And I can try to solve here. So if you want, we can actually write it as 1, 1 minus 1, 0 minus 1, 0, 1, 0, 2 times x, y, z is 1 minus 1, 3. And notice that I can actually, I could, so let me clean this entry. Right here, let's call this A, then the system is AX equals V, and I can, if I am also able to compute inverse matrices, this tells me that X is A inverse V, okay? So can I find what this inverse is? So it turns out that, by the way, these are the coordinates that are the coordinates of V with respect to B, where B is the canonical basis. And these are, what I'm looking for here are the coordinates with respect to the new system. So what we, and these, by the way, is the matrix that has, if these were B1, B2, and B3, what is this matrix? Is the matrix that has B1, B2, and B3 as columns. So what we have figured out is that if I write for a matrix for this B prime to be the matrix that has B1, B2, and B3 for columns, those are the vectors in the basis B prime, right? So B prime was given by 3 vectors. Then it turns out that the vectors in the, let's say B is the canonical one, then what we have is that if you look at this equation right here, these are the coordinates with respect to the canonical basis. So I have that if I multiply this matrix A, B prime times the coordinates of V with respect to B prime, what I am getting are the coordinates of V with respect to the canonical basis. And if I multiply by the inverse matrix, what I get is that the coordinates with respect to B prime will be the this matrix that we found inverse times the coordinates with respect to the canonical basis. So these two equations tell me that actually if I find the inverse, if I find this matrix and I find its inverse, then I can convert from the canonical basis to this new basis, and from this new basis to the canonical basis. So we can try to do that. In this case, the matrix was the matrix 1, 1, minus 1, 0, minus 1, 0, 1, 0, 2. And the inverse matrix, if you do the computation of an inverse matrix, is 2/3, 2/3, a third, 0, minus 1, 0, minus a third, minus a third, a third. So in particular here, we were talking about the vector 1 minus 1, 3. So if I multiply, if I use this part of the formula, if I want to find what are the coordinates with respect to my new basis, that will be the inverse matrix times the coordinates of V with respect to the canonical basis, 1 minus 1, 3, right? Yes. And then just multiply. So if I multiply this matrix by 1 minus 1, 3, I get 2/3 minus 2/3, that's 0, and 3/3 is 1. 0 times 1 is 0, minus 1 times minus 1 is 1, and 0 times 3 is 0, so I get a 1. And minus a third, minus a third, that is 0, and then 3, I get 1. So it tells me that the new coordinates are 1, 1, 1. Is that true? Well, that would be true if, let's see what happens if I add ones, the first vector, plus ones, the second vector, plus ones, the third vector of the basis. That gives me 1, 1 minus 1, that is 1. 0 minus 1 plus 0 is minus 1. And 1 plus 0 plus 2 is 3, which is V. So that is absolutely correct, that the coordinates with respect to the new basis are indeed the coordinates of this vector V with respect to the new basis B prime are 1, 1, 1. And this is true in general. So in general, if I have a basis which is E1 through En, is the standard basis of Rn, let's say, and B prime, B1 through Bn is another basis of Rn, then we put a matrix A with respect to this new basis is going to be a basis that has 4 columns. It has the vectors of the basis B prime. Then we have the following equations that for any V, the coordinates with respect to the canonical basis are in fact that matrix times the coordinates with respect to the new basis, and the coordinates with respect to the new basis are the inverse matrix of that matrix times the coordinates of the canonical basis. So these two equations are very important because they tell me how to translate coordinates from one basis to the other. In particular, they tell me that if I know the vectors of the new basis, I make a matrix, I make the inverse matrix, and if I multiply by the coordinates with respect to the canonical basis, I get the new coordinates. with respect to the new basis. For example, I can take in R2, I have the canonical basis 1, 0, 0, 1, the standard basis, and I'm going to pick a new basis, which is the basis 3, 2, 4, 3. And let v be the vector 1, minus 1, then we see that the coordinates of v with respect to the canonical basis are precisely those, 1, minus 1, and I would like to find the coordinates of v with respect to the new basis. Okay, so I write my matrix with respect to the new basis. It has columns that are the vectors of that basis. Now I want to find the inverse matrix. So what is the inverse matrix? Will be the inverse of 3, 4, 2, 3. I know how to find inverses. First of all, the determinant is 3 times 3 minus 4 times 8. So 3 times 3, 9, minus 4 times 2, 8. So the determinant is 1. So it will be 1 over the determinant times, and then 3, 3. I'm actually switching the entries in the diagonal and switching the sign of the off diagonal. So this is minus 4, minus 2, just like that. So the inverse is, in fact, 3 minus 4 minus 2, 3. And now the formulas that I had before tell me that if I want to find the coordinates of v with respect to the new basis, then I have to multiply by the inverse matrix times the coordinates with respect to the canonical basis. I have the inverse matrix. It's 3 minus 4 minus 2, 3. I have the coordinates of my vector in the canonical basis. I multiply and I get 3 minus minus 4, so plus 4, and minus 2 minus 3. So the vector is the vector 7 minus 5. Okay, so let's check that this is actually correct, that these are the coordinates. What that means, what these coordinates mean, is that if I do 7 times b1 plus minus 5 times b2, I should get v. So 7 times 3 minus 2 minus 5 times minus 4, 3, I should get v. This vector is 7 times 3, 21. 7 times 3, 21. So if I do 7 times b1 plus minus 5 times b2, I should get v. b1 is 3, 2, b2 is 4, 3. So this is 7 times 3, 2 plus minus 5 times b2, which is 4, 3. That vector should be equal to v. 7 times 3, 21, minus 20 is 1, and 7 times 2, 14, minus 15 is minus 1. And this is v, and that is exactly what was supposed to happen. That this linear combination gives me v, because these are 7 and minus 5 are the coordinates with respect to the new basis of v. So I do get the solution that I expected. So what we have done is just define what we call the coordinate mapping, which is the following. So we had V was a vector space. We had B a basis of V. And then what we've done is create a map from V to Rn that sends every vector to the coordinates of that vector with respect to the basis B. And note is that this map is 1 to 1 and onto, because for every vector, since this is a basis, there is a linear combination of the vector in the basis that gives me that vector u. Those coefficients are precisely what makes these the coordinates of this vector over here. So we know that there is, for every u, there is some coordinates of u with respect to the vectors in the basis b, and those coordinates are unique. So that tells me that it's 1, 2, 1, and in fact it is onto. If I take any vector in Rn, I can create a vector in V that has coordinates like that. So this map is what we say 1, 2, 1, and onto. And by the way, if I have a map, so any linear map, by the way, the map is map and linear. So a linear map V to W between two vector spaces. Notice that V was a vector space and Rn is of course also a vector space. A linear map between two vector spaces is an isomorphism. We say it is an isomorphism if it is 1, 2, 1 and onto. And in this case, if V and W are related by an isomorphism, then we say that V and W are isomorphic. And which means that they are vector spaces that may look very different. For example, here V might be some vector space of polynomials, but then we put them in coordinates and they look like Rn. So even though these polynomials and Rn look very different, they are actually sharing the same structure. And that's what the isomorphism says, that these two vector spaces would have the same structure. So let me give you an example of such a thing. So for instance, I can take V to be the polynomials of degree less or equal to 2. I can take B to be the basis, the standard basis of polynomials. Then P2R is isomorphic to R3 because there are three vectors in that basis that send polynomials to the coordinates with respect to that basis. So what the map does is that it sends a plus bx plus cx squared. It does send it to the coordinate vector abc, and this is an isomorphism. So then we say that P2R is isomorphic to R3. And for the applications, what this means is that instead of doing work in P2R, we're going to use this isomorphism, this map, to do work in R3 with vectors, which is a lot more convenient. So for example, if I want to show that the vectors 1 plus x, x plus x squared, and 3 minus 3x squared are linearly independent, then what we're going to do is convert these three vectors to coordinates and then work in coordinates. So here's the solution, is that I pick a basis. In this case, it seems just the standard basis would be the best choice. And then find coordinates. So this is going to be u, v, and w. So what are the coordinates of u with respect to these bases? That is the vector 1, 1, 0. The vector v with respect to that basis is the vector 0, 1, 1. And the vector w with respect to that basis is the vector that is given by 3, 0, minus 3. And then I want to figure out if these are linearly independent. Then u, v, and w are linearly independent if and only if these vectors 1, 1, 0, 0, 1, 1, and 3, 0, minus 3 are linearly independent. And either I'm going to prove that they are linearly independent, or I'm going to find a relationship, a linear relationship between among all these three vectors, which will give me a linear relationship among these three vectors with exactly the same constants. And I know how to figure out if these vectors are linearly independent. I just write the matrix, the matrix with those vectors for columns, and then row reduce. Because I'm going to, if this is I'm trying to solve AX equals 0, so I would do with an augmented matrix with zeros in the augmented column, but I can do it without that augmented column when it's just a homogeneous system. So if I row reduce, I get 1, 0, 3, 0, 1, minus 3. I row reduce, I get this, and this is 1, 0, 3, 0, 1, minus 3, 0, 0, 0. And that is actually already in row reduced form. And I see that there is a free variable. So these are actually, there is a solution that is non-zero. So these are going to be linearly dependent. This tells me that x is minus 3t, that y is 3t, and that z is t, is in fact a solution. So if I take, so the solutions are those, and that tells me that if I take, for example, t equals 1, it gives me a vector minus 3, 3, 1, which is a solution. That tells me that minus 3 times 1, 1, 0, plus 3 times 0, 1, 1, plus 3, 0, minus 3 is a linear combination that gives me the 0 vector. You can check that this is indeed 0, 0, 0. And that tells me that they are not linearly independent. And that also gives me a linear relationship, exactly same coefficients between the two, between the polynomials that we were talking about. So let's see that that is actually the case. If I do minus 3 times 1 plus x plus 3 times x plus x squared plus 3 minus 3x squared, what do I get? This is minus 3 minus 3x plus 3x plus 3x squared plus 3 minus 3x squared. And you can see that minus 3x squared cancels with 3x squared, minus 3 with plus 3, and minus 3x with plus 3x. So this is the zero polynomial. So the polynomials 1 plus x, x plus x squared, 3 minus 3x squared are also linearly dependent. Linearly dependent. Okay, and what we did is, instead of working directly with polynomials, which is a little bit cumbersome, what we did is work in coordinates. I just converted to coordinates, and in coordinates worked out that there is a linear dependence just using row reduction, and that gives me the linear dependence, and that linear dependence I can translate back into polynomials just to show that they are in fact dependent.